What is cloud computing? Cloud computing is the practice of using a network of remote servers hosted on the internet to store, manage, and process data rather than a local server or personal computer. Cloud computing provides on-demand access to services that can be managed without handling data servers. This is a more affordable option for businesses to adapt to due to its scalability and pay-as-you-go pricing. Cloud computing is offered by many large companies such as AWS, Google Cloud, Azure, and a few others. It provides unlimited amount of scalability, allowing you to increase or decrease space or instances that are used. Why is cloud computing important in cybersecurity? Centralized security management and monitoring. This means the security policies can be managed throughout all applications and services, making threat detection easier. Example, using IAM and AWS. Cloud platforms support automated security tools such as firewalls, intrusion detection system, antivirus scanning, and vulnerability management. Example, AWS network firewall. Third thing, data protection, backup, and recovery. It prevents data loss through backing up data and has continuous audit reports. It also provides group policy management to manage users in the company, such as IAM and AWS. This allows for people to be able to be monitored through their computer and manage logins and what they can access. Cloud computing is important in cybersecurity because it is a more secure way to manage applications in one resource. It is an advancement that many businesses are looking for. It is a cheaper but more secure option to manage and it requires less IT staff to maintain, reducing company costs as opposed to having on-premise data centers. Cloud computing. There are three types of services that AWS provides, such as infrastructure as a service, IaaS, platform as a service, PaaS, and software as a service, SaaS. And IaaS provides a virtualized computing infrastructure over the internet, such as virtual machines and storage. Example, Amazon EC2. PaaS offers a platform allowing developers to build, test, and deploy applications without managing the underlying infrastructure. Example, Google App Engine. Software as a service delivers software applications via the internet on a subscription basis. Example would be Google Workspace, Microsoft 365, and removes the need for local installation or maintenance. Change in cybersecurity with cloud. Before, cybersecurity was about securing a perimeter, but now it's about securing the data, apps, users, which are not confined to one location. Data can also be stored in different regions of the world that are available based on the cloud. The services you use in your cloud account is stored in a data center that the cloud provider owns and manages. These are the big three differences in the changes in cybersecurity with using cloud. Data breaches in cloud storage. What is data breach in cloud computing? A data breach in cloud computing occurs when a sensitive or confidential data stored in the cloud is accessed by unauthorized individuals. This can happen to various vulnerabilities, including misconfigurations, weak access controls, insider threats, and cyber attacks. The consequences of such breaches can range from financial losses to legal ramifications and damage to reputation. Some common causes of data breaches are misconfigured storage, like public S3 buckets, weak or stolen credentials, bad password practices, lack of multi-factor authentication, insider threats, employees leaking or misusing data, insecure APIs and applications, or poor encryption or no encryption at all. One real-world example of a data breach in cloud storage is the Capital One breach, where AWS S3 misconfiguration happened in 2019. The Capital One breach in 2019 exposed data of over 106 million customers due to a misconfigured firewall in their AWS cloud. A hacker exploited this flaw using a server-side request forgery (SSRF) attack to gain temporary AWS credentials. With these, they accessed improperly secured S3 buckets containing sensitive information like social security numbers, bank account details, and credit scores. The breach cost Capital One over $300 million in damages and penalties. This incident highlighted major cloud risks, especially the dangers of misconfigurations, the need for strong access controls, regular audits, and defending against SSRF vulnerabilities in cloud environments.
As of 2025, the leading cloud service providers are AWS, Microsoft Azure, and Cloud platforms by Google, AWS holds a major share of the market, offering a broad range of services such as computing power, storage, and databases. Microsoft Azure provides an integrated suite of cloud services that work seamlessly with Microsoft software products, making it an excellent choice for enterprise already using Microsoft solutions. Google Cloud Platform stands out for its robust infrastructure and strong capabilities in services like machine learning and scalable storage solutions. Identity and access management is a crucial aspect of cloud security, ensuring that only authorized users can access specific resources. IAM features include user authentication and authorization, ensuring proper access to cloud services. Role-based access control assigns permissions based on user roles, while multi-factor authentication adds a layer of security by requiring multiple forms of verification. Single sign-on makes it easier for users to access various applications with a single login, enhancing both security and usability. Key Management Services is a managed service that simplifies the process of creating, storing, and controlling encryption keys. KMS allows for automatic key rotations to ensure keys are not used for too long. It also tracks key usage through audit logs, which provide visibility into who used the key and when. Cloud providers offer a wide range of security tools and services to safeguard their environment. For example, AWS Shield defends against DOS attacks, while Azure Security Center provides unified security management across cloud workloads. Google Chronicle offers a cloud native security information and event management tool for quick threat detection and response. Additionally, firewalls and web application firewalls inspect traffic to block malicious content, while security groups and network ACLs control inbound and outbound traffic in the cloud. Cloud security services are designed to protect against several types of cyber threats. Unauthorized access is prevented through IAM policies, MFA, and SSO. Data breaches are mitigated by encrypting data and conducting regular security audits. DOS attacks are countered through traffic monitoring and automatic scaling. Malwares and ransomwares are blocked with continuous monitoring and antivirus solutions. Encryption is vital for protecting data, whether it's stored or in transit. For at-rest encryption, data stored on disk or databases is encrypted, ensuring confidentiality even if the physical storage is stolen. Common tools like AWS KMS, Azure Disk Encryption, and Google Cloud Encryption protects at-rest data. For in-transit encryption, data moving between devices or services is encrypted using TLS SSL, preventing eavesdropping and man-in-the-middle attacks. This is especially important for APIs, web traffic, and internal cloud communication. Looking ahead, we can expect several emerging trends in cloud security. AI and machine learning will improve threat detection, identifying anomalies and suspicious activities in real time. AI can reduce false positives, allowing quicker response to potential threats. Another trend is quantum safe encryption, which prepares cloud systems for a future where quantum computers could break current encryption methods. Lastly, Secure Access Service Edge combines network and security functions in a cloud native model, offering secure access regardless of user's location. It includes solutions like SWG, CASB, ZINA, and Firewall as a Service, which are key for remote and hybrid teams.
This slide covers the shared responsibility model. In cloud security, tasks are split between the provider and the customer. AWS, Azure, and GCP protect the physical servers, network, and built in security tools. Customers have the responsibility of implementing security options, protecting users through IAM policies, encrypting individual data, and patrolling their own assets for threats. For example, AWS protects the servers, but the customers must secure S3 buckets and IAM users. Misconfiguration like public S3 buckets are a major cause of breaches. Now, moving on to zero trust architecture. The idea behind zero trust is simple: never by default trust any user, device, or network. Always authenticate
every access attempt. Zero trust in the cloud means constantly authenticating both user and device identities, microsegmenting the network to limit movement, role based access control, and logging every move. For instance, a remote worker uses MFA to access Salesforce limited to their job role. Zero trust is critical for protecting distributed teams and public access environments. Next is compliance and cloud security. Compliance is mandatory but not optional. Firms must prove they follow regulations like GDPR during audits. Cloud providers help by offering compliance tools like AWS Artifact, Azure Compliance Manager, and Google Compliance Center. For example, a hospital on AWS can stay HIPAA compliant by encrypting data and using strong IAM policies. Cloud platforms make staying compliant easier and reduce manual effort. Finally, these are some best practices for adopting cloud services securely. First, manage identities carefully by using IAM roles and policies and always implement MFA for every user. Second, protect data by encrypting it and using protocols like TLS and SSL during transmission. Third, secure your network with firewalls and access control lists. Fourth, enable monitoring and alerts through services like AWS CloudTrail or Azure Monitor to detect unauthorized activity quickly. Fifth, perform regular audits to find vulnerabilities and update policies. And lastly, use cloud native backup solutions to prepare for disaster recovery. Following these best practices builds a strong security foundation, ensures regulatory compliance, and improves resilience against potential cyber threats.
Containers and Kubernetes in the cloud. So, cloud containers are software code packages that contain dependencies that are needed to run inside the cloud. They're essentially designed to run across every platform from the development to the production. Kubernetes orchestrate clusters of VMs or virtual machines based on the necessary requirements. So, essentially, Kubernetes make large numbers of containers easier to run. Containers and Kubernetes are both used in cloud development to improve scalability and reliability as they streamline application deployment and management. All right, so security risks and attack vectors. Our first one is image vulnerabilities. These are aspects like outdated software or insecure libraries that are able to let attackers gain access that is not authorized to the cloud infrastructure. Second one is insecure APIs. These are exposed API keys that allow attackers to limit legitimate users from accessing available resources. Attackers can essentially also overload these APIs, which can lead to service interruptions. Our third one is misconfigured RBAC. Role-based access control that is not configured properly can allow a user to be granted more permissions than needed, which in turn can expose sensitive data to them. This data can then be exploited. Lastly, we have pod privilege escalation. This grants a container more privilege than it should, which in turn allows an attacker to modify other pods that are within a cluster. Best practices for security. First one is image scanning. This is using applications like Trivy or Claire for an open source vulnerability scanner that can detect vulnerabilities or misconfigurations within containers. Second one is Kubernetes security tools. Applications like KubeBench or KubeHunter will check a Kubernetes cluster by running configuration checks that can ensure the best practices are being implemented. Third one is container runtime protection. Falco is one of many applications that focuses on monitoring what containers will do before they are deployed. That way, it can navigate suspicious behavior inside containers or Kubernetes pods for real-time behavior detection. Last one is network policies. These define how pods can communicate with one another and with other network endpoints. Essentially, only allow pod-to-pod traffic, start with zero trust, and use tools like Calico or Cilium to consistently test and enforce these network policies.